extend a to Dr. Radha Krishna Kavlu, our esteemed guest, for today's webinar on behalf of Symbiosis Institute of Children. I also welcome Dr. Vidya Patkar ma'am, our Deputy Director, and our Bhakti Teacher ma'am, our Placement Officer, and all the attendees of the event. Welcome, Dr. Kavlu, to SIG. It is indeed an honor and privilege to have you amongst us. I'm delighted to introduce you to our distinguished audience. With a rich background in space engineering and software development, Dr. Radhakrishnan Kavlu currently serves as a principal engineer for software and firmware at Dhruva Space, a leading space engineering solutions provider based in Hyderabad, India. In his current role, Dr. Kavlaru oversees various aspects of software development, including payload data processing, ground segment, software, workflows, and satellite mission design. Prior to his tenure at Dhruva Space, Dr. Kavlaru had a distinguished career at the Indian Space Research Organization, where he served as a scientist and project manager for the NASA ISRO SAR, which is the NISAR mission. During his 8-year tenure at ISRO, Dr. Kavalaru made significant contributions to artificial intelligence, satellite data processing, calibration, and the development of web portals for data dissemination. Notably, he led the ground segment activities for the NISAR mission, demonstrating his leadership and technical acumen. One of Dr. Kavalaru's most memorable experience was his deployment to Antarctica as part of the 38th Indian expedition. During his time there, he interacted with Indian scientists and gained valuable insights into end-to-end satellite technology. Dr. Radhakrishnan Kavalaru's extensive expertise and diverse experience make him an invaluable asset to our webinar. Today, he will be sharing his insights on integration of NISAR satellite data and spatial datasets for enhanced Earth observation, shedding light on the utilization of NISAR satellite data and spatial datasets for advanced Earth observation applications. Please join me in welcoming Dr. Radhakrishna Kavalaru to our webinar. We eagerly anticipate an engaging and enlightening session. Now I ask Bhakti ma'am to say a few words.
Thank you, Vedika, for your welcome note. Yes, dear Dr. Radhakrishna, it is a pleasure to, host you for the webinar series that we have for our students. It is in fact a pleasure, and that to thank you so much to spare your time on a weekend with us. Speaking about your introduction, she has given a very beautiful introduction. But something which I would like to say is, when I spoke with you, I came across the, the pleasure that you had always, you have dealt with you have always been fascinated with the space. You've always started, you are, currently now you're working as principal engineer at Dhruva Space, who are our hiring and recruitment partners, campus partners. But, what I was saying is you've been fascinated with space all the, throughout your life. And that is what brought you into this field. Your rich experience of ISRO, that too working on artificial intelligence and satellite data processing has been, it has spiced up and made your experience so rich. With all this, I would like to, welcome you for the webinar and looking forward for beautiful insights. These students are, let me tell you, these students are studying first year of their MSc and MTech Geoinformatics. Asmita might have told you already. And these are yet about to start their third semester, so they are already in their second semester now. So you can take it forward from here, sir. Thank you so much. It will be a pleasure hosting you. How would you like the session to be? Would you like the students asking the doubts in the beginning, or when you will be giving your presentation, or afterwards?
Yeah, hi. Firstly, can you hear me? And is the audio good?
Yes, your audio is perfect. How would you like the session? The question answers later on, or in
yeah,
between?
we can make it interactive, but it's not a problem.
Making it interactive, right?
Yeah.
Okay. That's lovely. That's lovely. It's a beautiful gesture. Thank you so much, sir. Now, please take it over, sir, from here. And Bedika, do you have anything to say after this?
No, ma'am, I don't have to say anything. Thank you, ma'am,
All
for the
right, all
enlightening
right.
words. And yeah, I hand over to you, sir.
Sure, sure, sure. Thank you so much, sir. Again, welcome.
Yeah, sure.
You
Thank
can
you.
take it
Thank you
away.
for such a great introduction, Team
Yes, yes.
Symbiosis.
Thank you
Uh,
so much,
there,
sir.
there's a small problem with my video. I hope it's not going to be a problem.
No, no, that's fine. That's fine. Would you like to share your screen or something?
Yeah,
Do you
I'm
need any?
sharing my
Oh,
screen. I'm going
okay.
to do that. Yeah.
All right, all right. Yes. Thank you so much, sir.
Give me 1 second. Just confirm if you're able to see the presentation. Yeah.
Yes, yes. We are able to see.
Right. Okay. So hey everyone, this is Radha Krishna, and as they have introduced me, I have a good amount of practical experience in building satellites and doing processing and building analytics and delivering those information or insights to end users. And yes, I've been a part of NISAR mission. That's a very very big Earth observation satellite. In fact, it's the costliest Earth observation satellite. There have been other satellites which are having higher budget like Hubble and JWST and others, but they're not Earth observation satellites. So NISR is a very very expensive satellite, and it's a synthetic aperture radar satellite. So I assume most of you are geoinformatics students, and you must have already been introduced to satellite images. And as I said, we can keep it interactive. If you have any doubts, you can always, stop me and ask me. Is my assumption correct that you know the basics of satellite images and all that, or do I have to, touch the basics? Can anyone confirm? Hello.
So
Am
these
I
people are
No,
aware of the basics which are taught to them.
okay?
But still, they would like to. They'll tell you about what all aspects have been taught to them. Someone from the technical team, if you can unmute and someone is trying to speak.
Sure. Uh,
One second. Huh?
yes, ma'am, we were just about to say that no, we know the basics of geo.
Sure. Okay. Okay. Fine. So I'm going to touch about synthetic aperture radar satellites. So the optical satellite imagery is what is mostly famous and mostly in use. It's let's say the passive remote sensing satellites, which capture the sunlight that is reflected off of Earth's surface. So if you see Google Maps, that's a set of high resolution satellites at different layers of zoom. Let's say at an overview, you'll see Landsat, and as you zoom in, you'll get Sentinel, and then there are higher resolution satellites which Google takes the data from stitches, color corrects, and then hosts it on their server, and then you see the sunlight reflected off of the Earth's surface, and that's basically passive remote sensing satellites. Now, when it comes to radar satellites, they are active remote sensing satellites, which mean they send their own energy to the Earth, and then they observe the reflected energy coming off of the Earth. And based on the reflected energy, they kind of make an estimate of how the Earth's surface looks like. So these kind of instruments are called um, time of travel cameras. Okay, so these are also cameras because these instruments can estimate what is happening on Earth, but that is basically dependent on the time of travel of the light that is being sent by the radar. So these are called time of travel cameras. And yeah, let me just touch upon so this going to be two presentations. One of it, the first half is going to be very quick introduction, engineering introduction to synthetic aperture radar. Yeah, so why we call it synthetic aperture? Because If we have a static aperture, or if we have a normal aperture, what we don't have basically is high resolution. Okay. And why is that a problem? Because if your antenna size is very small, your resolution is actually going to be affected, right? So if from space, if you're at a distance of NISR is going to be, I think, at around 700 to 900 kilometers. So at that height, if you're having an antenna aperture, uh, and you want to get satellite images in meters, your antenna size itself should have been in kilometers. But that's not really possible with respect to engineering. We cannot build an antenna which is of hundreds of meters or even in kilometers. So what we basically do is we make a virtual aperture. So as satellite moves in orbit, we kind of accept signals from the first pulse also. So let's say the first pulse was sent at t0, and the reflected emissions are coming off of time at a lot of intervals. When the satellite moves for hundreds of meters, again we accept those pulses also. And because this is going to be a virtual aperture, we call it a synthetic aperture. So this is basically synthetic aperture radar. That's how the name comes. We'll see all that. um, Right. So, how do we? So basically, the synthetic aperture is only in the azimuth direction. So as satellite flies from north to south, the synthetic aperture is going to be in the line of flight direction. But on the range direction, which is across track, it's going to be like a normal radar, right? So how a radar works is basically you send pulses. So on this diagram, I'm not going to touch on the mathematics part, just the concept part. So you have a short pulse and we have a long pulse. So irrespective of what kind of pulse it is, a radar works based on pulses. So you send this pulse and the next pulse and the next pulse and almost all similar pulses. And when you hit these targets that are there on ground, these pulses are supposed to come back to the sensor, and based on the time of retrieval of the pulse, you basically estimate the time, the distance between the instrument and the target. Okay. Now what happens is, if your pulse is very long in time, if your pulse is very long in time, it is short in frequency, right? So what happens is, if your pulse is very long in time, it cannot differentiate between two very closely separated objects. Okay. Because if they are so closer than the pulse time itself, the pulse time is going to engulf this both of these objects. So if you want to improve your range resolution, what is usually done is very short pulse. Okay. But when you compress your pulses, or when you shorten your pulse time, what happens is the energy that is sent per pulse comes down drastically, right? So here the energy is going to be what is the energy? It's going to be the integration of power with time here, right? So the energy is large but the energy is small here. So what we basically try to do in radar for a good range resolution is compress your pulse as good as possible for a good range resolution, but give it as much as power as possible. So that's about it for range resolution. And there will be contours. So contours are basically the same time responses. So if your beam width is like this ellipse, and if your targets are in this particular contour, it means that your targets might have been anywhere in the circle. So you need to compress your contours so that you get a particular target location, right? So that's how you do it. So you basically do draw two contours, and then you kind of compress your ranges, right? And you'll understand all of this once we see the synthetic aperture radar images. Right. So this is the range resolution that I was talking about. You send your pulses in the range direction. So this is range. This is the radar flight path. and this is the range direction, and this is the azimuth direction. This is the flight path. So here is what we are doing pulses, right? And this is the synthetic aperture direction, which is the radar flight path direction, right? So as I told you, what we particular kind of do is we compress the pulses. So as I said, the if your impulse response is S of t, power into your power you send into impulse response will be received power, and then you'll have your range resolution equation and all that. So this is the compressed pulse, and you send that power. And your radar range resolution will basically be dependent on the speed of light into the time of the pulse divided by 2, because you are doing 2 times the travel of the same distance upwards and downwards, right? And then what happens is this is a compressed pulse, right? So this is a very small pulse. Now, there are lots of compromises that we've got to do when we are doing the pulse transmission with respect to power and with respect to frequency. And also, because we are trying to do a synthetic aperture and we are also trying to do a range compression, we need to modulate or code this particular pulse. So we need to put some information in that pulse to know when this particular pulse was sent. So let's say at T0 I send a particular pulse, at T1 I'm sending a different pulse, at T2 I'm sending a different pulse. So you need to know what kind of what pulse was that when it got reflected, right? So you need to modulate it, and that's why we call these a chirps. Okay, so if we are not modulating it, some things like a continuous wave radar also we can do. So frequency modulated continuous wave radar is also possible. And then there are chirp radars. Chirp radars means in your pulse you actually fit some kind of chirp. So this is a linear frequency modulation chirp function. So this is the pulse that you will look at, and in the frequency form, if you Fourier transform it, this is how it's going to be. So any synthetic aperture radar satellite, when it goes overhead, if you have a spectrum analyzer in radio frequency, you can actually do an amplitude analysis, and then you will see the chirp function, and thereby you can also analyze what satellite it is and etc. Okay, so this is with respect to chirps on the range direction. I'm going to just skip all this and I'll just go to azimuth direction. So yeah, so this one concept is, because you're actually looking from the platform in an inclined angle, the distance that you will be getting is basically inclined distance, right? This is what time of travel looks like if your target is here. So what we call it as slant range. But what you want is on the ground, what is the distance? So for that you need a small correction based on the incidence angles, and that is what sine theta is for. So that is slant range versus ground range. So initially when you do image processing, you will get it as slant range product, but then you do your correction for the pulse responses, and then you get a ground range product. Now, coming to the next position or next dimension, you've got an along track resolution. And as I said, this is a virtual aperture, right? So this is a synthetic aperture that we're trying to do. And exactly what is going to happen is, see, there are 3 points in the flight path. Okay, and here is the target. You've sent one pulse from here. Okay, and then you can actually receive the response at B and C. Okay, so it means the antenna is as big as the field of view for this particular target. So for example, if the first pulse was from here and the last response was heard at C, so the antenna is big as AC, right? So that is the length of synthetic aperture. So how many times it has looked at this target is what we are seeing, and thereby we can also increase the received strength. And again, there is along track resolution, and it always depends on how much time that you're looking at, and because it is synthetic, you can actually modify it and all that, right? And this is all available in textbooks, but this is the concept. Okay, and there are multiple modes in any synthetic aperture instrument. There are aerial instruments as well, and then there are satellite based instruments as well, but the physics and the image processing is same. Okay, so when I say strip map or spotlight, let's say spotlight is what is Spotlight, I'll just give you one example of a spotlight mode. So spotlight mode is basically you use the whole imaging uh, orbit, or let's say the path from, let's say here you have a start and here you have an end for imaging. From here to here, you actually look at only one point or one place of the earth. Okay, so you tilt your antenna, or you tilt your phased array of the radio sensors, so that it looks at only one target, so that you get most of the resolution over there. So that is spotlight. So it's like the floodlights that are there for celebrities on stage. And there are strip maps, which is basically scanning the full earth beside it. So it, for strip map, it is actually scanning every parallel area around it. Okay, so this is strip map. So there's going to be unfocused also. Unfocused is basically you look at only once, and then there is no compression and all that, right? And then there is fading SAR and all that, right? So, and then you do your calibrations, basically how much radiation you are sending, how much you're getting reflected based on your ground calibration. So finally, what you get at satellite is basically, I'll show you an example from Indian data. So can you see the screen of Bunidi that I'm able to show? Can anyone confirm?
Yes,
Yes,
sir,
sir.
we can see.
Right. So recently we actually launched a satellite. ISRO launched a satellite called EOS-04. Um, okay, and this is a synthetic aperture radar satellite. And what I want to show you now is the response or images how we capture from a radar satellite. So this is a portal where you can see everything in live. I am trying to show you for yeah. So this is a false color composite image, and so this is basically made from two different polarization accepted. Okay, so how is it made is basically the colors that you're able to see in one color. It is basically H polarization in the radio frequency sent and H polarization received, and in the other color it is basically H polarization sent and V polarization received. Okay, so when the radar satellite, the satellite, so for here the satellite may be based on the incidence angle. I'll just zoom out and show you. So this is some data over Ladakh, right? And Ladakh, say it is going Himachal Pradesh, Uttarakhand, Delhi, etc. So the satellite, because it is a range resolution satellite, so it has to be essentially inclined because it's a radar. The satellite must have gone from left side from here or right side from here, and the antenna will tilt to scan this area. Okay, and when it scans this area, it sends energy, and based on the reflected energy and based on the time of travel, it actually predicts from which part of this area the energy has been received. Okay, so this is what it is. The and most of it is grayscale, so black and white imagery per band, because we are sending in one polarization and receiving in one polarization. We are able to capture a false color composite, right? So now what we are able to see is what we will understand, and for that, let's go to Sentinel 1A, which is a C-band synthetic aperture radar. And here in the drop down, you can also access this. Actually, this is free. In here, you are able to see VH and VV. VH is basically V sent, H received. VV is V sent, V received. So I'm sending only V polarization from satellite, and I'm receiving H and V polarization. Okay. So let me add this, and this is 1st March. So this is yesterday's data. Let me see where the data is captured for yesterday. Okay, so there is data over Gujarat. So let's go for Gujarat and Bombay. Bombay is also captured. So let's just zoom in on Bombay because it's a city. We can see a lot of features. Okay. So first thing you can think about is why all the water is very dark, right? Here, all the Arabian Sea is purely black, correct? And the ships can be easily identified. Very, very sharp. Ships are easily identifiable. And even if you go zoom in, you can see how big a ship is, the ship responses, and all that. And because this is radar, what you can also appreciate is these are side lobes. Okay, so whenever you send a pulse, you do a reverse Fourier transform from the responses. What you're seeing is the side lobes. Just like how you put a specs, your lens acts as a Fourier transform, and you see lens glares, right? So this is also radio frequency lens glare, you can assume. Right. So one thing you can understand or think about is why all this is black, and why I am telling all of this for something that I have to tell about NISR, right? And also in the city, when I zoom in over the city, what you can see here is a lot of responses there wherever a lot of big buildings are there. Okay. And when there is rivers and when there is moist areas or gardens and all that, you're not having such a high response. Okay. So this is a C-band radar, and it is the resolution is around 10 to 15 meters, the ground resolution. Okay. Now, just have this in mind, and we will progress to NISAR. So in NISAR, what is the speciality is basically in NISAR we have a L plus S band radar. Okay. For NISAR, actually, the best website that you can see is the official website. Excuse me. In the official website, you'll have a lot of detail, and you can just go to mission website. Here we are having two bands. As I said, for Sentinel it is C band, but for NISR it is L plus S band. So what are all these bands, right? So let's do some exercise and let's see what is all this band. So for that, what we can do is radio frequency bands. We can just type this, and we'll have a Wikipedia article or a radio spectrum you can open, right? And you can do this all. So just do this exercise yourself also, because this may be important nevertheless, because you're a geoinformatics student, right? It will definitely be important if you're essentially going to communications domain or doing analysis of ground station, getting satellite data, analyzing in roles after your program at Symbiosis. So you have different uh, radio frequencies, and these are radio frequencies. So you've got starting from extremely low frequency to very high frequency, terahertz frequency, and all that. Okay. So now coming to this is high frequency VHF, UHF. So most of amateur communications, or you see small antennas, right? All that happen in VHF and UHF. Okay. Then you've got band. So this is increasing frequency, that is increasing energy. So as you increase your energy from radio, this will go to infrared, and then it will go to visible. Okay. So you can, on an electromagnetic spectrum, this will be on the right side because these are low energy waves compared to visible, and after this going to becoming visible, infrared, visible, and then ultraviolet and x-rays. So this basically how why these are useful, that is the one important thing, and I will also show you why these are useful. Okay. So by seeing this particular strip of image, this is a C band radar, right? There is no single cloud that is visible, right? Everything is a response from land, but where is the cloud? There is no single cloud is visible. And this is the speciality of radio waves, because in clouds the water molecules are very small, and these radio waves are bigger, or at least the size of water molecules, so these can penetrate clouds and atmosphere. So all responses you'll get is basically from ground directly. So that's why we use radars to escape atmosphere and clouds. So what I was showing you was C-band radar, which is 4 to 8 gigahertz. Okay. Now what we are trying to build is, and we already do have some satellites which already work in L band, which is ALOS, Pulsar, and we've got other satellites as well. Okay. But they are not very systematic, and some of them are very highly priced. And for S band also we've got satellites. Okay. But again, they are highly priced, or they are commercial, right? So now what is the speciality of L band and S band is basically, for L band it can do a lot of biomass studies, and it can actually penetrate even a lot of ground layers also. Okay. And S band is actually used to study soil moisture, etc., right? So on NISR, what's going to happen is both of these instruments are going to be built together. L band is being built by NASA, and S band is being supplied by ISRO, and they have been integrated into the satellite called as NISR. Now what's going to happen is, for this particular image that you're able to see, which is a C band. C band, you're able to see VH, VV, right? In NISAR, what's going to happen is there's going to be an S band VH, VV, and there's going to be an L band VHVV, right? So different, two different frequencies in one different SAR, but in each different band or each different frequency, you're going to have multiple polarizations. Okay, so there's going to be enormous amount of data from one satellite from different frequencies in radio spectrum and different polarizations, right? So as I showed you for EOS 04 in MRS, as I showed you, there was a color image that was just from one band, one radio spectrum. So there you will be getting all this information from two different spectrums, and then it is going to give a lot of data, and we can do multiple types of analysis. That's what we're going to see, and this is the speciality of NISR. So I'll just show you the satellite. So this is the satellite, how it looks, and this is the radar. So this is the antenna, okay, and this is the RF electronics, and these are the solar panels. So the RF electronics actually control what kind of chirp that we've got to do, what is the bandwidth, and what is the energy that we've got to send, and this is sent to ground from this particular antenna. Okay, and then back again it is getting received, and again it is getting processed and stored. Okay, and there are two different electronics integrated into this particular uh, uh, electronic subsystem, both for L and S. Now, one simple exercise we can do is I will take you all through ArcGIS story maps. Have you heard of or have you ever worked on story maps from Symbiosis? This student batch who are attending this talk, have you worked on story maps?
No, sir, actually, we didn't go through that.
Okay, no problem. So story maps are basically just interactive website and maps and satellite image integration. So I will just go through. So if you can scan, like what I'll be showing you is how you can use NISR for floods, and this is actually applicable for other SAR satellites as well. But for NISR, I'll be focusing in particular for floods, wildfires, land subsidence, oil slicks, and glacial motion. So this is the QR code. If you scan, you will actually go to the story maps for floods. Okay, I will just stop here for 3-4 seconds before going into applications. If you have any questions till now on what I've spoken, we can discuss, and then we can proceed. Any questions till now? Okay, I don't see any questions. So if you can scan this floods QR code, you will actually go to the story maps, right? So how can we detect flood events with SAR? And this is a good read for all of you. You can actually do a lot of research also. There's lots of papers and it's all active. And flooding is a very, very prevalent situation, especially in India, even more than Western countries. So there's lots of research that is happening. Now, how to interpret SAR flood images is what we'll see in detail, and this is a good exercise for anyone to do. There's lots of flooding in Chennai. There's flooding again in Bombay. There is flooding in Assam. There is flooding in northern states like Uttarakhand. So you know when it floods, all you have to do is download satellite images, Sentinel-1 or EOS 04, and then do your analysis as we will do right now. Okay, so what happens in a SAR, right? It is basically sending radiation and getting the reflected radiation, as we have seen in this case also for Sentinel 1A, right? The satellite is sending radiation and it is getting the reflected radiation. So when it sends the radiation, water being a good reflector, actually if the satellite sends radiation, the water will reflect radiation away from satellite. So satellite is not getting any radiation back from water. That's why it is, marking it as low radiation received. Okay. And when you have a building or something like Bombay has, some of these buildings actually reflect radiation back to satellite, and that's why there is a lot of high reflection. So water, whenever there is pure water, there is no wind and all, you will see it as dark black, pitch black. There's no wind. But wherever there is wind, like here, you are able to see some disturbance, right? What is this? Is basically probably because of ships or because of wind. The water surface got disturbed, and based on the waves, based on the structure of the top layer of water, some radiation got reflected back to satellite. Okay. Now, what happens in floods is there are different types of surfaces, right? So if there is a river is going to be purely black. Okay, so it's going to be static, it's going to be black, so it's not going to reflect back radiation to the satellites. It's going to be black. You can detect it as a flood. Okay, just let me zoom in. So you can detect it as a flood. But then if you, because it's a flood, it means some water has come out of the large water body into non-riverine areas, right? So if there's some amount of low vegetation, okay, so this is the yellow box. Let me show you the yellow box. So this is yellow, right? So this is the low vegetation area. Here what is happening is water is prevalent, and that's why it's still dark. Vegetation is not doing any much of radar manipulation. In non-flooded trees, which is blue, you are able to see it's not really dark and it's not really white too. Okay, it's non-flooded trees, right? But in flooded trees, what's going to happen? You see, this is red, right? We would never have imagined that non-flooded trees and flooded trees would be such drastically different. Okay, so why this happens is radar, the water reflects away from the satellite, but again that radiation that is reflected back away from satellite again gets reflected by trees multiple times, and a lot of radiation again goes back to satellites. Okay, so that's why this dark white area is flooded, this dark black area is flooded, and this short vegetation area is also flooded. Okay, so if you see a lot of areas with your own eyes, you will be able to capture this better. Okay, now we will see two different maps. This is on September 17, 2018, September 23, which is 6 days away. As you can see, there's a river that is flowing over here. This is the river that is flowing. The flooding happened through that river, and all this dark white is basically forest areas have been flooded by water. Okay, and there's been flooding over here and multiple places as well. If you have scanned that QR code, you can actually follow me and interact also. Now you can see this is an optical image, right? And as I go through, see how optical lens are offering us completely different ideologies, right? Information itself is different. So here, this is a river which is green, right? So there's some kind of vegetation there already. Now in SAR, that you're able to capture it clearly, right? So here there's vegetation and then there is water too, right? And now you see after 6 days how drastically it has been flooded. Almost whole area on the left side is flooded, right? So all this actually you can detect it with various deep learning algorithms. Detecting black area is straightforward, but detecting this vegetation is flooded is a little bit difficult, and for that you need a lot of training data. There are data sets which have actually been made for specifically detecting floods. Something like, I'm just giving you pointers for further work. So something like Sentinel-1 to flood dataset is a deep learning dataset, which is actually very good benchmark. You can train your models on this, and I think most probably it should straightforwardly work on L-band and S-band datasets as well. But if not, you can use some amount of transfer learning there. Okay, now this is about floods. So it's straightforward detection is for black, but for flooded vegetation or any other areas, a little bit of training might be required. Okay, now we'll go to wildfires. So how wildfires are affected now, because we've thought about water, wildfires are also a little bit similar. So this is the qr code. But I'll also again stop here for people to scan, and if you have any questions, you can ask me for floods, till floods, anything. Okay, moving forward, wildfires. It's a very very big disaster or an event in Western world. Not not very prevalent in our areas or our regions, but yeah, in Mexico, South America, and North America, and even in some parts of Europe, wildfires are very very prevalent. So what happens is, during rains, thunderstorms, or even summers, very very dry seasons, forests catch fire. Okay, and because forests catch fire, what happens in SAR responses is as follows. Okay, let me just show you what happens. This is the map. Okay, so this is wipeable map. On the left side, it's not affected by wildfire. On the right side is affected by wildfire. So what is happening here is the vegetation itself is going down, right? So there's leaves are going down, branches are going down, reflections are going down. So a lot of radiation which were earlier getting reflected back to satellite will now be reflected away from satellite, because there are no leaves to scatter your radiation to the satellite, right? So this is all going to become dark. So based on the change detection, you can actually detect what part of your forest or conservation area has been affected by wildfires. Okay, and it's going to be the same or similar for any other forest based change also. So you want to detect deforestation, or you want to detect biomass changes. A very very big trending topic is carbon credits. Have you grown new forests? Have you grown new crops? Or have you decreased forests? Is what governments and private companies are also interested in. One very big industry that is focusing on this is aviation industry. You must be wondering, how come aviation and forests are linked, right? What is happening now is, because flights are burning a lot of aviation turbine fuel which is harmful for society, they are buying carbon credits. So these are some packaged instruments which are being sold in form of a proxy for growing organic forests. So someone is growing organic forests, they are observing it through satellite imagery, making a certification, then selling it to aviation companies as a carbon credit. How are they doing it? Everything is through satellite imagery and ground knowledge. So this is a very very big industry. Lot of startups are coming in, lot of roles will be there in future. In coming 1 2 years, it's going to boom, right? So knowing this is a good thing in geoinformatics. Okay. Now moving on to land subsidence. Very, very, very big use case for NISAR and interferometry lovers. I'll stop again here for 3 4 seconds before moving forward. Cool. So this is land subsidence. So interferometry is a very, very beautiful art. Okay. So what happens is, you have satellite, you can take repeated pictures of the same area. So before, you have a particular path length, but let's say the land has moved, the tectonic plates or something has moved, the structure has moved, then your path length in the later date images will differ. What you then do is, you take this interferogram, I mean you take this path and you interfere it with this path. So then you will have a interferogram, you will get some fringes. Okay, and based on that you can actually detect how much amount your ground has moved. Okay. Based on that, there's also detection of aqueducts as it's happening, aquifers, how much groundwater is there and all that. Okay. So based on phase differences, these are the fringes that we see. So if someone knows good amount of physics, how interferogram works, how interferometry works, this is a great area for you all to get into. Again, the industry is very very big. People are actually building products who are monitoring flyovers, structure of flyovers with satellite imagery, because with NISAR and even with Sentinel, the changes on ground that you can detect is in the area or is in the order of millimeters. So with NISR, if the ground has moved in the order of millimeters also, you can detect it. So a geotechnical engineer, let's say you want to become, you can actually become a very, very good geotechnical engineer with a good interferometry experience. So land subsidence is again another very, very big use case for NSR. And for NSR, you don't even need to do interferometry yourself. You don't need to do any software. The government, NASA and ISRO themselves will offer you land subsidence products. So once NSR is launched and the commissioning phase is over, you can actually go to the Bunidi website from ISRO or ASF DAC from NASA, and you can download large subsidence products. How much the ground is moved directly, you can download, and it will be like this color map, as I have shown here, the color map like this. And then from there, you can actually see how much the ground has moved. Right. One more big, very big industrial application. Okay. Then there is oil slicks. Right. So we'll be moving to oil slicks. And these are oil slicks or oil spills, again very, very big industry. Navy, Coast Guard, and then fishery organizations, everyone want to monitor it. A lot of environmentally sustainable goal development and all that come into place, because if you drop oil somewhere, oil leaks somewhere, a lot of destruction is going to happen for animal life, coral reefs and all that. Right. So how do you detect this? Basically, again, purely water response. Right. So because water has a certain kind of response, water does not reflect radiation back to satellite, but if oil is there, what's going to happen? Right. Again, if you do polarimetric analysis, a clear distinction can be observed like this very clearly. Oil spill is there, correct? Oil spill is there in water. So such patterns you can actually detect from machine learning algorithms, and you can actually do very everything automatically. So now what is happening in today's world is basically people have built algorithms and they are running in cloud computers. There are no people who are monitoring manually, and somewhere some oil spill is happening in southern Atlantic or northern Pacific, you'll get an alert on a mobile phone saying some oil spill has happened. And based on that and based on AIS data, they'll detect which ship is responsible for this, and then they'll take necessary action. Right. And glacial motion. So again, these are very, very small examples. There are very other examples as well, but these are story maps that I'm showing you just for you to relate. Right. Again, as I said, glacial motion, glaciers move a lot like rivers, but they are solids. Right. So again, because they are moving, you can detect your movement, and based on glacial motion, you can actually predict floods, you can actually predict rivers, you can predict how much agriculture will be there in the state of Uttar Pradesh based on the glacier availability in Uttarakhand. Right. So once you know the glaciers, you can actually predict everything. Right. You can even predict, because the economy itself is dependent on agriculture and the cost of inputs. Right. Based on glaciers, you can actually predict what is the kind of GDP that India is going to have. And yeah, some people have done that also. So yeah, like from SAR itself, you can see how the glaciers are moving. Right. So this is a literally movement of glaciers. Now, in short time scales, it's not possible, but on a longer time scales, you can see this. Right. All this is solid, but still it moves. That's what glaciers are. Right. And yeah, so from UAV SAR interferogram, you can see it. So these are interferograms, as I said, fringes, as I said, right? So you take a T1 image, you can take a T2 image, and then you take a interferogram, and based on the fringes, the blue color, the pink color, you can actually color code. So pink color is close to zero movement, and the blue color is higher movement. So here there is a higher movement, here there is a higher movement, etc. So that's how it is. So from the phase difference. So once you unwrap your face, you can actually get how much the glaciers are actually moving. Story maps. If not, in your system, you can actually go through the story maps. References here for papers, how to do this, and what are the softwares to use for interferograms, what software to use this for, polarimetric analysis and all that. So that's how you do, this is a very, very basic and NISAR, and how you basically use SAR for Earth observation applications. I think that's it from me. I think this is a very, very huge topic. If I've been, exhaustive, if it's boring, excuse me, but if it is interesting for at least some of you guys, I think you're going to have a lot of fun in coming days. Yeah, that's it. Also, if you have any questions, I'm open. You can shoot it.
Thank you, sir, for this wonderful session. I hope everyone found the information valuable and engaging as well. So now we would like to move on to the question answer session. Here are some of the few questions from the students. I would like to go on one by one. Okay. Um, so the first question we have, what are the benefits and challenges of using two different radar frequencies, L band and S band, to measure changes in Earth's surface and ice masses? It is from Sukanya Chakrabarti, MSc Geoinformatics.
Yeah. So as I said, L band is majorly used for biomass. Okay. L band can actually penetrate a lot of leaves, and L band can also penetrate some amount of soil as well. But for ice, for my perception, both of the responses in L and S must be similar. Okay. But where you can actually see the difference is where the thickness of ice is very less. L band must penetrate a little bit, but glacial motion and interferometry, both of them must be almost same, is what I am assuming. And this is the first satellite which will have concurrent L and S band for Earth observation. Similar to this, we had another mission, which is Chandrayaan. On Chandrayaan, we had a DF-SAR, dual frequency SAR, which is again L plus S band. But that images, if you see, it is all based on the lunar minerals and lunar texture and lunar dielectrics. So yeah, this is the first time we are flying, and we are estimating only, I think, biomass is going to be different.
Uh, okay, so sir, we will move to our next question. Next question is from Tuhin Pal MTech. What are the potential applications of NISAR data for urban planning, infrastructure development, and disaster management?
Yeah, so urban planning. I mean, if you see urban planning, it's going to, usually it requires a lot of high resolution data. NISAR is going to be, I think, at best 7 meter resolution. At 7 meter resolution, what you can actually do is basically, if you have a DEM, you can predict the low lying areas, high lying areas. You can actually predict, let's say, water flow, watershed, all that. But you don't have high resolution data. Hardly you will, I think, be able to see small buildings. So not very, very big use cases, but some amount of use cases. But for disaster management, yes, as I told, floods, wildfires, oil spills, and a lot of different things like that. Disasters, yeah, go NISAR.
So, sir, we would like to move to the third question. That is, how can we leverage NISAR data to address critical environmental challenges and promote sustainable development? It is from Shayok Roy, MSc Geoinformatics.
Right. So sustainable, I mean, most of the applications for NISR, especially from biomass perspective, right? So you can detect, there's lots of agriculture applications as well. So what kind of crops are growing, what is the soil moisture, right? So, and then, deforestation, afforestation. And not just that, you can actually work on mangroves, you can work on sea wind velocity, surface wind velocities, and all that. So a lot of information you will be able to get from NSR, which will actually directly be inputs to your environmental modeling, which will actually give you how close you are to your SDGs.
Thank you, sir. Now we would like to go to the next question. How does the integration of NISAR data with spatial data sets improve Earth observation capabilities to enhance the precision and accuracy of geospatial analysis? It is from Costa Pramani, MTech.
Hmm. So NSR satellite data itself is a spatial data, right? What you can consider NISR data is it's a data filler. Okay, so wherever there is no L band and S band information, where today there is no systematic coverage of biomass information or land subsidence from any satellite. Allows Pulsar itself, it takes a lot of time for you to cover that particular area if you even if you task it, right? So what you can imagine NSR as a very very good data source provider. After getting the data, you build your analytics and extract those analytics into your own formats, let's say raster or vector format, and then you include these analytics into your engines of application, whatever application you're working on, right? So NSR is going to be a good data filler for any different application that you're working on, is what I can tell.
Thank you, sir. Now we would like to move our next question. What are the computational challenges associated with processing and analyzing large volumes of NISAR data in conjunction with other spatial data sets? It is from Shayok Bhattacharjee, MSc Geoinformatics.
Yeah, so NISR is going to be one of its kind for satellite data processing. No one in the world, any agency has processed this scale of data. NSR is like a 12-day repeativity satellite. Every 12 days, it's going to see the same area. So we've got interferograms, we've got covariance matrices, and all that as products. Till now, for Sentinel, users generated interferograms on their own computers. Now for every imaged area, agencies will generate interferograms, agencies will generate covariance matrices, agencies will generate single look complex information, images, and all that. It's going to be very very hectic. And it's already been estimated it's going to be petabytes, 20 to 25 petabytes per year, and a lot of this is going to be done on cloud. So yeah, it's a very very hectic architecture with respect to software processing and all that. So as complex as it is, the NSR satellite itself is a very very big complex engineering marvel, and on the ground also, ground stations across the world, not just in India, but we've got ground stations across the world in almost all different continents. The data comes, the networks are all blocked, and then the data has to reach the processing station or the cloud. Cloud processing has to happen and go to users. Users also, because we are doing all this because users will not have big computers to do interferograms, right? So all the cloud processing happens and users directly download interferograms. So this is a very very big software architecture as well. I think the complex software architecture ever, even bigger than OpenAI.
Okay, so sir, we would move to our next question. That is, can we use this data set to predict flood susceptible zones using ML and deep learning techniques? It is from Masood Karim, MSc Geoinformatics.
Yeah, I think that's a good problem statement to work on. Before flood, I mean, what I've spoken to you is post flood detection to report to authorities or to take some action. But if even before floods, also, if you have a DEM, you can actually predict where the flooding area might be. So we call them as FHZ, flood hazard zones. So you can, yeah, you can work on that, and I think it's a very trending topic and a good research direction as well.
So our next question is, what are the applications of NISAR data in security and law and order? It is from Sahil More, MSc Geoinformatics.
Yeah, when it comes to security, again, you have to think about it how you want to use it. I don't think NSR is meant for security, but I mean, I can think about some applications in ship detection. So ships are readily available, I mean, visible in NSR data. More than that, I think at 7 meter resolution, I don't think any other vehicles or anything else will be visible. So yeah, I mean, I think water organizations can use it, Navy, Coast Guard, etc. But I don't think they will also, focus on NISA. They have their own satellites. Yeah.
So this is our last question, sir. Studying land subsidence using SAR data infragram, can anyhow earthquake predictions be made for regions where earthquake is quite active? It is from Anish Shelke, Impact Geoinformatics.
Yeah, I think yeah, you can do that, and there's lots of research that's been done in that direction as well in land subsidence. Earthquake prediction, yes, it's being done. Land subsidence is not just for earthquake prediction, but also for landslide prediction and security of big structures. Okay, very very big structures, like let's say the stadium, Gujarat Stadium, or your Bombay Stadium, etc. So wherever your big structures are there, which are having high stresses and high loads, yeah, you can use that, and not just for earthquake prediction, but also landslides and all that. So wherever geotechnical inputs are needed, yeah, interferograms. You go for interferograms.
Thank you, sir, once again. Now I would like to call Gayatri Gurumurthy to share the vote of thanks.
Good evening to all of you. My name is Gayatri Gurumurthy. On behalf of the Symbiosis Institute of Geoinformatics, it is an honor to have had the opportunity to deliver this vote of thanks to Dr. Radha Krishna Kavaluru, our esteemed guest speaker for the webinar on integration of NISAR satellite data and spatial datasets for enhanced Earth observation. First and foremost, I want to express our sincere gratitude to our esteemed speaker, Dr. Radhakrishna Kavaluru, for his insightful presentations and for sharing his expertise with us. Your knowledge and passion have enriched our understanding of the huge impact this integration of NISA satellite data and spatial datasets for enhanced Earth observation can have. I would also like to thank our director, Dr. T.P. Singh sir, and also our deputy director, Dr. Vidya Patkar Kumbar, ma'am, for giving us an opportunity to host such an enthralling and invigorating webinar. This webinar has provided much food for thought that will make us delve much deeper into the sea of knowledge of integration of SAR data and Earth observation data, thereby providing a path for further analysis that can be conducted using such high quality satellite data. Furthermore, I would like to acknowledge the hard work and dedication of our placement officer and the entire placement organizing team, whose meticulous planning and attention to detail ensured a smooth and seamless experience for all the participants. Their dedication and commitment to providing valuable opportunities to our students are commendable. And I would like to extend a heartfelt vote of thanks to everyone who joined us today for the webinar, asked their thought-provoking questions, and contributed to the overall success of this webinar. Your enthusiasm and curiosity are what make events like this so rewarding. Your engagement made the event more interactive and truly enriched the learning experience for everyone involved. Last but not the least, I want to thank everyone behind the scenes, Bhakti Thita ma'am, and the webinar team, and all others who worked tirelessly to bring this webinar to success and fulfillment. Once again, thanks to you, our esteemed guest speaker, for sharing his expertise. We are grateful to all the participants for making this webinar a resounding success. Your presence and involvement have made a significant impact on the success of this event. In closing, let us carry forward the insights gained today and continue our journey of learning and collaboration. We look forward to future engagements with all of you. Thank you once again for your participation and support.
Thank you. Bye bye.
Thank you, sir.
Thank you, sir.